we move now to Xavier, I think. So he's going to give a perspective on how observations and models can improve our knowledge. So Xavier, he's a ICREA research professor and head of the Climate and Health Group at ISGlobal. He's a task team member of the World Meteorological Organization Climate and COVID expert group, and also expert group member of the Health and Climate for the Union of the Mediterranean. His research entails with the interplay between climate and health, where he attempts to uncover how climate impacts on a wide range of diseases. Thank you, Xavier. The floor is yours.
Okay, thank you, Cristina, and thank you to the organizers for inviting me, in particular also the TipESM office in the DMI, chaired by Erika and Chiara. So thank you. I'm going to talk not so much on monitoring, but on the applications and the use of this ocean information, in particular on predictability of climate tipping points, and so on disease models that make use of this enhanced observation system. So essentially all we'll deal with how ocean research and improved monitoring is improving our understanding of the climate crisis and what is so crucial. And I'm going to present TipESM, which is exploring tipping points and their impacts using Earth project, having around 13 partners of different countries in Europe, also having NCAR and NOAA as external partners, among other groups. And also at this point, it makes use of what might be the most advanced group of Earth system models that participate in ISIMIP 6 and now also contributing to ISIMIP 7 and under the guidance of the Danish Meteorological Institute. So tipping points have made it to the press recently because of a few escalating number of papers, some of which authored by partners in TipESM. And essentially, the objective is to try to provide more understanding, more knowledge on what are the factors giving rise to those tipping elements, and also how close we are to these tipping elements crossing a threshold and becoming reversible or irreversible. We are also connecting to impact modeling in terms of ecosystems and societal responses, and with an interest in generating and improving early warning systems, and also helping stakeholders to derive safe emission pathways. So about tipping elements, this is the question: how close we are to these thresholding events, and how reliable, how robust are those early warning systems. And among those, there are a number of them that form the Earth system and that we know that are closer or further to tipping. So here there is a scale of warming. You don't see that quite well. But essentially, there are some of these elements that we know of the climate system that might be closer to a tipping. So the intensity of the red color denotes the likelihood of this tipping occurring. And so the idea is also to explore the mechanistic dynamics behind those elements, and also understand how the rates of warming and the duration and intensity of these global warming dynamics might facilitate or not the tipping of those elements. And reversibility is of course one of the important aspects, essentially because some of these systems are said to be close to this change of regime. Among those, we are concentrating not only but essentially on those ones that presumably are closer to tipping. So these massive loss of ice sheet, essentially in the northern pole, the AMOC and the subpolar gyre collapse, the Amazon and tropical collapse, also the dieback. In this particular modeling exercise, we at ISGlobal are also involved in the permafrost thaw, and also any other tipping elements that we might not know and that might come from the ESM simulation. So the idea is also to get a deeper understanding on all the cascade events, the positive feedbacks that might occur and that we might not be aware of yet. So at ISGlobal, I will show also an example of an outcome that improves with an enhanced ocean observing system. We also work on El Niño sound oscillation, as this is also one of the tipping elements known to feedback on many other systems, and in particular the Amazon rainforest, which is also another submodel with which we are also working in TipESM. So TipESM will inform the main panels, like also Chiara mentioned, so the next IPCC, the biodiversity panel, World Climate Research Program, and with an intention, with an idea of providing information also on risk indicators and alert signatures that might be used by a stakeholder to try to keep the world apart from those dangerous pathways. So the key methodology is to explore the results of a number of overshot experiments in which, in comparison to baseline pre-industrial conditions, so the suite of models are run at the rate of warming that's similar to that accumulated to now. So this 0.2 degrees per decade, which is achieved differently depending on the sensitivity of the different models. And essentially, it concentrates on two levels of warming, so 2 degrees and 4 degrees of warming. At this level of warming, the simulation is ramp off, and so it's stabilized. And we then analyze the results in terms not only of global warming projection, but also of the important elements of the climate system. So in addition, and after some time of this stabilization runs, the models are derams, so that means we extract CO2 at a similar rate at which the model is warming in the beginning. So in this case, at this 0.2 degrees per decade, and this is done with different speeds, so different acceleration, in order to give stakeholders different kinds of pathways for recovery, and also to try to see whether some of these tipping elements reverse or they are irreversible. So as an example, I was going to explain one of the uses in which we have benefited from improved ocean information. In particular, we've been studying the origin and predictability of El Niño sound oscillation, that in TipESM is one of these important predictors of some of the other cascade events. And just only as an example, we developed a statistical state space Kalman filter model that is now being added to the long-lived forecasting plume, and it makes a prediction beyond the spring barrier of 9 months. And what we can see here, I only highlight one result, which is the capacity of the model to simulate better when the TOGA information was added to so that means the tower array, the TOGA core system. And this is denoted by not only the time, but also the close matching the magnitudes of the El Niño events in particular, because it is concentrated only on the world cases. And conversely, you see that in the pre-TOGA period, the model makes far worse in approaching the magnitude. So this coincides also to, as I said, to a post-TOGA when the TOGA program was implemented. We see also a decrease in the model error, and which can also be seen in the slope of the regression between observations and forecasts. If we split these two periods of time, and we see how there is an increase in the slope of those regressions, denoting that the model makes slightly better. So this model uses some wind stress predictors in different areas in the tropical ocean, but also it makes use of some varying predictors that span the southern Pacific Ocean and going deep to levels of up to 500 meters. And again, this temporarily helps improve the capacity, the skill of the model in forecasting events with a persistent win that you can see in the recent period with regard to the former period. So another example is that when we add these 250 meters, 300, 400 meters deep information, we try to predict individual events, and when we go towards the present, you cannot see very well, but both coefficients indicate when these come up as skillful predictors into the model, and these tend to happen much more often in the recent times, and that's because of a gain of information. So quickly, I'm not going to delve into details. We use this information to try to nudge climate-sensitive disease models, not only by doing that in areas where El Niño sound oscillation has some predictive skill, but also because this enables us to predict temperature and precipitation in those areas, which also can be used in a multi-scale system to forecast, for instance, dengue incidents in South America, essentially, so in different places in the continent, also in Thailand. And just not to be always talking about ENSO, I'd like to highlight, for instance, that other ocean areas that will benefit from the enhancement of monitoring systems also have a role in, for instance, malaria in Northwest India. One example of this is the South Tropical Atlantic, where we see that also in atmospheric PRCP, so prescribed atmospheric experiments, that it originates a kind of Matsuno-Gill atmospheric response that impacts in the form of modulation of the southwest monsoon, that then is the one that affects the rain, the wind with moisture and rains in this area of India, where vegetation and malaria are highly correlated. There is a high spatial coherence, and nicely what we see is that when we surpass, so this cannot be seen, this is NDVI, so vegetation index indicators, that when they surpass a threshold, this is around 0.2, you see malaria incidence rising, and below that threshold, the system disconnects. So that's an interesting example. Another one using ENSO for malaria in the East African highlands. Also, just 2 points of interest that link to the observations. We have El Niño sound oscillation index, El Niño index right here. So, and we have malaria in the highlands. There are two different kinds of malaria vectors. And what we see is that there is a nonlinear relationship between El Niño and malaria. So there are responses to some events. Some other events do not promote the same kind of response. And that's also a mirror of how different El Niño events are in the record and how different they are from the composite pattern. So, yeah, we can use mathematical model of malaria in this case, make use of this information and try to derive skillful predictions that in this case of the highlands, because the highlands are not limited by rainfall, have to do with temperature. And we see also thresholds in the response of malaria to some vegetation and temperature changes, so that we see increases and decreases and switching off of the responses. And we can make use of these for a stakeholder information. So with this, I finish. TipESM, you have the website where you can consult also on our aspect of the project. Thank you.